Let's start. I posted some stuff this weekend, so still haven't graded your first homework assignment because I was doing these other things. But so one thing I did put up was a sample for test number 1, which is coming up next week, right? So now be careful that you read the disclaimer, right, about the test 1 sample. So in particular that it's probably longer than the test, okay? So if you work on that and you think, oh, this is really, way more than I can get done in, in the amount of time for the test, that's fine, right? It's supposed to be that way. So I tried to get, I think, all the different kinds of problems that that we might that we're hopefully that we'll get a chance to talk about before next week, but I'm not sure that my my anticipation here may be off a little bit. So, but I don't think we'll cover more. Well, we won't cover more than the different types of problems that are on the sample test. So lots of things here are kind of going to be familiar to you, and they're just things that we talked about at length in the notes, right? So you may have to refer back to your notes for some definitions, like in problem 2, it says why isn't this game this familiar game, right? Why is that not a combinatorial game? So how does that miss the definition of being a combinatorial game? So if you look in the notes, there's when we were going over notes, we probably didn't stress that a lot in class, but there's a definition of combinatorial games in there, so you can take a look at that and see how this misses. So that's a pretty straightforward question. For those of you who don't know rock, paper, scissors, you can just look that up on the internet. Okay. There are explanations of how that game goes. All right. One's a little bit harder. That just says what's it describes a winning strategy for this game of NIM, this version of NIM, which has lots of variations on it, and just ask you to demonstrate why this particular strategy is a winning strategy for one of the players. So I think it's going to be pretty easy to see that that's a winning strategy. I think you'll be able to write down explanation there pretty easily. This is just a question about Latin squares, so that's just seeing if you know the definition of orthogonal Latin squares. That's pretty straightforward. Okay, so that one's easy. So some of the questions are just definitional in nature, and then some of them are going to be a little bit more challenging. In particular, the counting sorts of questions. All right, that are at the end. All right. So again, these are a lot of questions, so this is more than what you would expect on a test. But now I do want you to note there the format of some of the questions, okay? And we've been sort of stressing this in the notes, but you're probably in the homework problems not following these particular instructions. So the sample test is good in that sense for a little practice in following these instructions. So here's a pretty simple counting problem. And we've just started talking about these examples, but we have a lot more examples to look at. So it wants you to form a 7-letter word from these letters, okay? So just that simple letters there. But the restriction is that the vowels must be adjacent to each other and must be preceded by an even number of consonants. All right, you'll know the difference between vowels and consonants, right? Okay, so in this list, A, E, and U are vowels, right? And the remaining letters are consonants. Okay, so that's just a fairly straightforward counting question. But it's going to ask it in a kind of a roundabout way, right? Because it's going to say, oh, okay, so write design a model here for this set of W's, this set W of words that we're trying to count, all right? So it's going to ask you to build some model that corresponds, right, to the set of words. And then, ideally, you would be able to use our facts from that we've learned about set theory here and cardinality of sets, right, to count this set. And since this set is a model for this one, right, then you would know the cardinality of the set that you're interested in, right? Okay, the set of words that meets that restriction. All right. Now, the second part of this says just to show that your model is valid here. Demonstrate how an element of your model corresponds to a word, right? Your model set is not probably going to be a set of words, okay? All right. The set of words that you're interested in here, okay? But the model set, there'll be a way of taking an element from the model set and using that element in the model set to construct a corresponding word, right? So what you would describe is, here's an element of my model set. So your model set might involve cross products or things like that, right? Here's an element from my model set. Here's the word that corresponds to that element from the model set, okay? Right? So here's how I know, right, that my model set corresponds to, or there's a one-to-one correspondence between my model set and the set of words. All right, so we're going to we've been doing a few examples like this, but we'll see more examples today to make this a little bit more clear. All right. Now, what we didn't discuss is the second counting method, so we're going to get to that today. Okay. This is our set theory sort of a way of counting sets. And that's very useful at times, okay, but it has limitations. So today we're going to discuss yet a second way of counting sets, one that's probably more familiar to many of you who have some experience with counting sets, okay, and that is this algorithmic way of counting sets. So part 2 says, describe an algorithm that you can use, an algorithm, right, a series of steps, correct, like a computer program. Describe an algorithm that you can use to create an element of this set W, okay? All right, so what would be a series of steps, right, that you could use to put together a word from this set, correct, okay? And then if you know how to count the number of executions, the number of possible executions of that algorithm, then you can also count the number of words in your set, okay? Because each different execution of the algorithm should give you a different word, okay? If you've gotten a proper algorithm, all right? So if you know the number of executions of the algorithm, then you'll know also how many words there are in the set, okay? So that's sort of the second basic method that we're going to use for counting sets, okay? And this one is useful at times when your set method is not useful, but vice versa. Sometimes the set method is very useful when it's not so easy to describe an algorithm, okay, for building the elements of the set, all right? And then, with those two things in mind, right, then you just want to count the elements of the set. And then we just add some further restrictions here, right, and ask you to count those sets. But you don't have to build models for these, right, okay? You don't have to build models for these. All right, whoops, now why didn't the spell checker catch that? All right, I don't know, okay, because I don't think that's a word. All right, so I'll see if I can fix that. So there are lots of counting problems kind of like this, right, okay? And then some of the counting problems, though, are just straightforward counting problems, all right? So you can do it by building a set model, or you can do it by creating an algorithm that allows you to create elements of the set that you're interested to count, or sometimes it's a mixture of the two, okay? Some of these counting problems, though, are a little bit tricky, so a few of them you may have to just do by exhaustion. So it may, but what I mean is just by inspection. You may have to just actually sort of think about every possible element of the set that you're interested in and count them that way, okay? Some of them you won't be able to use sort of these shorthand techniques that we're describing. Okay. Hopefully those sets won't be too big, because if those sets are really big, then you're going to have trouble, counting them by inspection, right? By just trying to figure out, what's every possible element of that set. Okay. All right. So there's the sample test. Yeah. So, this is just a sample. This is not to turn in. But don't forget, your homework also, right, is also a material you want to use to prepare for the test. Yeah.
So the disclaimer said that not every topic that will be on the test will be on the sample test. But will you list those topics for us to know exactly what?
No, I think every topic. Oh, I see. Anything in the notes, right, that we've discussed in the notes is potentially on the test. I think most of those are reflected on the sample test, okay? No, I don't have a list of sort of all the things that we've talked about. That's just part of the notes. Yeah, right. But most of the topics that we've covered are somewhere reflected on the sample test. Maybe not every detail of those topics, right? Okay, but I think they're all pretty much there. Certainly, I think most of the different types of counting problems are covered on the sample test or the homework. So don't forget the homework also, right? Okay, is a possibility. All right. So anyway, so let me fix that mistake. So I'll fix the spelling mistakes and double check this by this afternoon. But you still got your homework number 2 to think about, right? In the meantime. All right. So on the homework, on the homework there, let's see if I can get back to where I was. I did post the solutions to the first homework. So the solutions to the first homework are here. All right. So for you to examine there. Now, keep in mind, when I write the solutions, right, I'm trying to put in an incredible amount of detail so that when you read the solutions, you will be able to understand the solution. So I think I hope that I got all of these written down in such a way that the solution is clear from reading that. But you're not expected to create that amount of detail, right? Okay, in all of your answers. So don't think that your answers have to look like this to get credit. Okay, right, all right. In many instances, when I grade, I'll just be looking for sort of the idea, right? That if you can express the idea, that results in the solution of the problem without, completely describing that ideal perfectly in formal mathematical terms. But I think in most of these problems, I did that, okay, and avoided a lot of hand waving in these solutions. So I think they're all correct. But if you think one's not correct, then let me know. All right, okay, to any of these. So I'll post also the solutions to the second homework at some point. I've started working on those, but still have a ways to go on that. That brings up the second homework. So I wanted to at least entertain questions. I may have to take some questions under referral, though, for next time. So if y'all have questions about homework 2, I've only worked out the only ones that I've written down the solutions for so far. Some of them are pretty straightforward. Like I think there's solving a Sudoku puzzle, right? So I think that's you know how to do that, right? Even if it takes you a little while to solve the puzzle, or executing that de L'Alubert algorithm for building a magic square. That's just a matter of following that algorithm, okay? And the last 2 problems, the game problems, I did already write down the solutions to those, so I can explain those in details. Are there other or we can discuss those in detail. Are there other questions that I need to think about between now and Wednesday that y'all want to ask about in particular? I want to warn you about the last question, okay? The game question, poison cookie, okay? So just if you're struggling with that particular game, okay, there's a reason for that, okay? So that's a famous, a notoriously famous game, okay, for a particular reason, all right? So what does it ask you there? See if you can find a winning strategy?
Yeah.
Yeah, okay, all right. So that's easier said than done, all right? So just a warning about that one. I wouldn't, it's fun to think about that game, but I wouldn't spend a lot of time there looking for the winning strategy on Poison Cookie. What's the one before that one? Oh yeah, Cunan. So Cunan now has, yeah, you can find a winning strategy for Cunan, okay? The hint I will give you on Cunan, though, and this is often true of games, is play the game backwards, all right? So think of what is going to be a winning position for black or white at the end of the game, okay? And then can you reverse engineer a winning strategy, okay, from what you know is a winning position at the end of the game, okay, for one of the two players. I think that's the key to finding the winning strategy for one of the two. I think on this game, it gives you two versions of the game, right? I think in one version of the game, the first player wins, has a winning strategy. In the other version of the game, the second player wins, has a winning strategy. But I'm not sure which version is which. I can't recall. Okay. Yeah.
So what you're saying about Poison Cookie, not to spend too much time on it, does that mean there isn't a winning strategy?
No, I didn't say that. No.
Or is it simpler than it seems or something?
No. It's both of those things. Yeah.
Okay.
Yeah, that's right. It's kind of a conundrum. So it's a famous example. So, but it's fun to think about and get frustrated by, and then see what the and then see how to think about it carefully, so you can figure out why you're frustrated by the game. Okay. Yeah. All right. So I won't say any more than that for the time being. I was trying to think of, so we'll discuss the solution. I was trying to think of other games. There must be a ton of them, like Poison Cookie, that has its same characteristics that makes it interesting. But I couldn't think of another one off the top of my head. But there must be lots of examples of games like this. Okay. All right. So it's actually the difficulties in finding the winning strategy for Poison Cookie actually make it kind of a fun game for that reason. Fun to play. Okay. So y'all aren't asking me for. All right. So what about? Let me ask you then. So some of these that I thought that were not straightforward, right? Like 14. Is that one hard? Have y'all tried that one? Why there are only 8 magic squares of order 3? The basis for that is knowing that, and we did this in class, right? Knowing that 5 has to be in the middle, exactly in the middle square. Okay, so you can use that fact. You don't have to derive that fact again. That's in the notes. Okay, so does it follow quickly from that fact that, well, I don't know how quickly, but at least does it follow from that fact that there can be only 8 of these, all right, magic squares. And I think 42, I think that one's fairly doable, okay? That's a tiling problem, but I think you can figure out why that chessboards of that description do not have a perfect cover. The one that's given there is a good one to experiment with, okay, then you can generalize from that why those sorts of chessboards don't have perfect covers. So those two I know maybe are worth bringing up again on Wednesday. Okay. All right. Well, all right. So I think, so let's plan on Wednesday, at least for turning these in, okay? And so, and then we'll see where we're at, all right? But again, the homework 1 solutions they're done, right? They're posted. So if you're interested in how many ways there were to color that cube, or how many perfect covers there were of a 3x4? 3x4 chessboard? I think that was one of the problems. Well, the answer's there, I think. So, so you can take a look at that with the reasoning for why that's the right answer. Okay. All right. Let's go back to our notes then. So we have a lot to do, but these problems are, I think, a lot of these are taken from the books. Not all of them, but a lot of them are taken from the book, and they're all fun. A lot of them are fun. Yeah.
Are we going to get our homework ones back?
Yes. Yeah. So I do have to grade your homework and give it back to you. Yeah, for sure. Okay. So hopefully that will be by Wednesday, but no later than Monday. So, yeah. All right. And hopefully I can get the homework 2 solutions posted quickly too, maybe by Wednesday, so that if you turn that in, then you'll have the solutions immediately. The sample test solutions I'll also post, but it won't be until I don't think it'll be till the Monday at the earliest on the sample thing. So see what you can. It's not going to be. What's a little bit frustrating about that sample test is it's not going to be immediately clear in many of the problems if you have the right answer or not. So you're going to come up with a solution, and you really cannot check your work. All right. So there's really no way to work backwards and verify that your answer is correct. So until you see the solutions, there's going to be a little bit of anxiety there, right, in knowing whether you did the problem right or not. Okay, that's just the nature of combinatorics problems. Unless it's kind of like show this, then if you show something, you're usually pretty convinced that whether you're correct or not, right? But if it's just how many items are in this set, and it's a really big set, then it, maybe kind of a mystery whether you've done that properly or not until you actually see an answer posted. All right, so now in these problems, again, remember, we're talking about building models, set models, to represent the sets, right, that we're trying to count, okay? And in many cases, the set model will be very, very similar to the set itself, okay? So there'll be almost no really difference between the model and the set, okay, right, that we're interested in. But in some instances, the set and the model are not going to correspond exactly, and then you do have to understand, how do I take an element out of the model and use that to, and match that to an element in the set that I'm trying to count, correct? But in this problem, I think the elements of the model and the set itself that we're trying to count are really close, all right? So we want to know how many words of length 7, okay, can be formed from these letters, all right? So how many words of length 7. So now notice you're going to have to repeat letters, correct? Okay? So there's no restriction that letters are not repeated here. You can get a word of length 7 right out of these 5 letters, these 5 Greek letters, right? That's the first, alphabetically, the first 5 letters of the Greek alphabet, okay? So that's alpha, beta, gamma, delta, and epsilon, okay? I think they'll show up in one of your sample test problems as well, okay? All right, so the symbols, though, are kind of not important that these are from the Greek alphabet until a little bit later, okay? These are just 5 distinct symbols, right? And we're trying to build words, right, which is just an arrangement of the symbols, correct, in a list, right? An ordered list, right? An ordered list, correct? The arrangement of the letters in the list matters, right? So that's what we're trying to build here, okay? So what's a model that we could use for this set? 7 what there? Well, so 7 alphas, that's one of the words, okay? right, that we can form, right? Okay, so that's not a model for the set of all words. That's just an example of a word in our set, okay? Do y'all want to give the set that we're trying to count here a name? That might be a useful idea, okay? That's frequently a useful thing to do in mathematics, right? Something that you're trying to work with, right? Give it a name so you don't have to be spelling it out in words, okay? All right, so what do y'all want to call S? All right, okay. Oh, S for 7. I was thinking W for words, but that's fine with me, right? Okay, so S there is the set of words, right? All right, so that's a set that we're trying to count, okay? The link 7, right? I'm not going to put link 7, but it has link 7 there, right? And now we want to create the model, right, that that we can easily count, hopefully, right, that we can easily count, but which has a one-to-one correspondence between the items in the model and the words in our set S, correct? Okay, but again, I think the model and the words are going to be they're going to be very close to each other in this, for instance, right? Okay, so so let's call that model set M. Any suggestions there on how to create M? Oh, so you want M to be what now?
Like
an integer segment from 1 to 5. An integer segment from
1 to 5.
Oh,
5 letters.
okay, all right. So just 5 there, right? So there's my notation for integer segment. So M, I don't think, is a model for the set of words, correct, right? Okay, but it might be a set that's useful to us in building the model, correct, right? Okay, because this obviously has cardinality what? 5. And this clearly has cardinality a lot more than 5, okay? In fact, you can find 5 elements of this set really easily, Kaylee, by doing what? You mentioned one of them already.
Just making all of the 7 letters be the same
letter, that's right, okay. Right, just make a word with all the same letters, right? So you can have 7 alphas, 7 betas, 7 gammas, 7 delta, and 7 epsilon. There's already 5 different words, right? Okay, but that's clearly just the tip of the iceberg, right? Okay, yeah.
So in the model, like 7 alphas would be 7 ones?
Possibly, right, okay? So that's a good idea, right? So you're thinking, so really, M here is not really a model for S, right? But M is really a model for what? The letters, right, okay? So M is really there, a model for the letters, right, okay? There's a correspondence between, or you can think of a correspondence here between these numbers, right, and these 5 letters, okay? It's a really good correspondence, too. The only thing we really care about in this class to have a correspondence is there are 5 things in this set, right? And how many are there in this set? 5, right, okay? So that's enough in combinatorics to have a correspondence, all right? But it's really a better correspondence because these things have a natural order to them, right? The numbers, of course, 1, 2, 3, 4, 5 have a natural order, and these letters also have a natural order, right? Okay? It's the Greek alphabetical order. Alpha, beta, gamma, delta, epsilon. That is in alphabetical order in Greek, as I understand it. Okay, don't speak Greek, but I think that's correct. So, so actually, the correspondence is very strong, right? So this is really a good, I think, a good model for the set of letters, right? Okay. We don't have a symbol here for correspondence, but let me use double arrow, right? So this set sort of corresponds to, not sort of, right? This set corresponds to this set, right? The set of the 5 letters, correct? Okay. So they're not equal, so I cannot put an equal mark here. They're definitely not equal, right? But there's a one-to-one correspondence, right? And probably the one-to-one correspondence you would think of is 1 corresponds to alpha, 2 corresponds to beta, 3 corresponds to gamma, and so forth, right? Okay, so, all right, so there's some progress, but we still have to build a model for all of S, right? Okay, so now what?
A set of 7-digit numbers, since we're using M for an integer segment.
Do we have to do a set of top one?
We have to actually build a set, though. Okay, yeah, all right. So, so what operations do you know that we've used for building sets? Cross products, right? Okay. I guess we also have unions, right, and complements, correct, right? And cross products. That's really about it. Okay. Well, we also had partition. We're going to get partition's going to be important to us, but the simple ones are things like complement, union, and cross product. Okay. All right. So which of those shall we try? Cross product, right? Okay. It's going to be a cross product, right? So what is going to be our model set? I need a new name for the model here. W? Okay, all right. So what cross product is it that y'all have in mind? Here's what I have in mind. Is it 7? 1, 2, 3, 4, 5, 6, 7. Exactly right, because we want words of length 7. I guess we can write this as m to the 7th power, right? Okay. Now, do I know how big m is? So that's really crucial. I'm sorry, do I know how big w is? That's really crucial, right? Okay. Is that obvious? Well, we have a theorem to help us with this, right? So the cardinality of W there is going to be what? Perfect, right? It's going to be the cardinality of M raised to the 7th power, correct, right? And we know what the cardinality of M is. That's trivial, right? That is 5. And so there it is, okay? The size of that model is 5 to the 7th power, all right? So we're hoping, thinking, right, that what's the case? So what do we want the size of S to be? 5 to the 7th power, right, okay? We want S also to be 5 to the 7th power. But, all right, here's the step that's in the sample test, right, okay, that I need for you to think about. Look, so if you wrote down 5 to the 7th power, you're going to get the right answer, okay, because that is the correct answer. But the step I need for you to think about is, why is that the correct answer? So why is there a one-to-one correspondence between W and S, okay? So why are S and W equivalent in that sense? There's a one-to-one correspondence between those things, all right? So, again, I'm going to write that down using this notation that I just made up on the spot, but that's okay, all right? So I need to know why are S and W, right? Why is there a correspondence between those two sets, okay? This is again the question that's asked repeatedly in the sample test. It says, show how an element of your model corresponds to an element of the set you're trying to count. So what we want to explain, and it doesn't take much explanation, but why does an element of this cross product, how can you use an element of this cross product and derive a word from that, right? Okay, right? See what I'm asking? So, because what do the things in this look like? So what is an element of M? 1, 2, 3, 4, 5, 2. Yeah, it's going to be a what? What are these things called? Begins with a T. It's going to be a tuple, right? In this case, what size tuple? 7 tuple, right? So it's going to have 7 coordinates, right? And those coordinates are all going to be what? From M, right. So you'll have something like 2, 3, I'm just making one up, right? 1, you can repeat a 2, right? You can repeat these things, right? Okay. So there's just an example of an element from M, right? Okay. But what word does that correspond to? No, this is an element of M, Eduardo, so it corresponds to a word in S. Not a set of words, but just a single word in S. So what word in S does this match up with?
Beta, gamma, delta, alpha, beta, epsilon.
There you go, right, okay. That could be beta, what?
Gamma,
Is this gamma,
delta,
delta,
alpha,
alpha,
beta,
beta,
epsilon, epsilon.
epsilon, right. Right? Okay? So why is that so obvious?
These we haven't like 1 to 5 from 8 or alpha.
That's right. See, we have a correspondence, right, between M and our set of letters, correct, right? 1, 2, 3, 4, 5 corresponds to these letters alpha, beta, etc., correct? So this tuple of numbers 1 to 5, right, we can match that up with this word, right, where we just replace each number by its corresponding letter, and then collapse it into a word. Don't write it as a tuple, because you usually don't write words as tuples, right? Okay? So just write it as a string of characters. Does that make perfect sense, right? So for every one of these tuples that you can think of, right, Eduardo, you can easily do what? Match that up with what?
A letter in the Greek alphabet.
No, okay? For each one of the tuples, tuple in the set, what is it, W, for each one of the tuples in the set W, we can easily match that up with a what? Word, right, okay? We can easily match that up with a word. And vice versa is true as well. If I give you a word, right, can you then tell me the tuple that would correspond to that? Sure, right. So, well, here's, did I write down one? What if I write down all epsilons? 7 of them. Yeah, it would be 5, 5, 5, 5, 5, 5, 5, right? Okay, or 7 5s, correct? Okay, exactly. So, indeed, right, there is a one-to-one correspondence between these tuples and these words, okay? So, these sets have the same size. That's the key thing, right? These sets have the same size. Well, we know, though, how big W is, right? Okay, because we have that theorem that says, tells us about the size of cross products, right? So now we know how big S is as well. That's what I'm getting at, right? Okay. So, see, that's all kind of rather obvious. If you were actually counting the set S, you would probably count it correctly. I think you would come up with 5 to the 7th power. But I need you to get a little bit under the hood of, in your mind, what's going on in your subconscious. This is what's going on in your subconscious when you discover that, when you figure out that S is 5 to the 7th power. This is really what's happening in your subconscious. But it's so elementary that you're not thinking about it explicitly. Okay, your brain is, but it's not in your conscious mind. Yeah.
So is it enough to show that a tuple in S corresponds, or a tuple in W corresponds to a word in
Yes.
S to show
Yeah.
that they're
Right, yeah, that's what's asked for in the sample test. Just explain why, when I look at an element of my model, and sometimes the elements of your model are going to look, not in this case, here the elements in the model do look very similar to the words, right, okay, except we have a tuple as kind of a string of numbers versus a string of letters, right, but those are very similar things, correct, but sometimes your model, the elements of your model look a lot different than the elements of the set you're trying to count. They're quite dissimilar, all right? And then this understanding this correspondence really becomes important, all right? Okay, well, now let's see if we can do some of these easier ones. Now, when I say build a set model, that's a little bit simplified. Sometimes your set model, you might have to your set model might have to be a union of a couple of simpler sets, or sometimes you might right? So it's possible your model might be 2 sets that you're combining into a union. Or sometimes your model might be a little bit too big, just a few elements too big, and you may say, okay, here's my basic set model, but this has a few too many elements in it, I'm just going to subtract those out. That's fine for a set model, okay? But you can't have to subtract too many elements out, because then that would be too far away from being a model. But if you're just one or two or a handful of elements, too many in your model, and you know what those are, that's a fine set model. You can just say, okay, the size of the set is this, but I have to take away these few things, okay, which really shouldn't be in there. All right. So when you build a set model, don't think it's just one gigantic. I mean, if we really got careful, we could form it as one set, but in practice, that's not really the way you're going to do it. Okay. All right. So I'm going to let y'all try one here. Okay. How many words begin with begin or end with alpha? Okay. So how many words there begin or end with alpha? So you may be able to count it really easily, and but then again, try to think about a really legitimate set model there. Okay, did y'all arrive at something? Am I going too fast there? Let's see how you thought about this. So any suggestions on, anybody have a suggestion on where to start?
Two sets.
Two sets. Okay, so I like that. Okay, what are those two sets?
I labeled them M prime and M double prime.
Okay, so M prime and M double prime, right? And so what were what are those? Can you explain? Tell me what those are? It may be a verbal explanation. That's fine.
The M prime is when alpha's at the front.
Oh, so this is words that begin with alpha? No, I'm sure you didn't do it wrong. Okay. I think what you're going to describe for me is the model for this set. Okay. All right. So, but I'm going to actually think of the set of words first. Okay. And then we'll write down what is the model for that set that we can count. Right. Okay. So I think you naturally collapsed two steps, but I may be anticipating here wrong. What?
I think I made two sets where I only needed to make one because I put M prime as being a set of 4 integers because whether alpha's at the beginning or at the end, you know that you're only going to have 4 integers to choose from besides alpha because that's already set.
Okay. All right. All right. So yeah. So. All right, but let me proceed here, okay? All right. So let's let M prime be the words that begin with alpha, and then I think M double prime is the opposite of that, right? Isn't that words that end with alpha? Something like that? All right. So that's an actual set of the words, right? Okay. So if you want words that begin or end with alpha, that's the set that we're looking for. Then how do we combine these two sets to get that? Yeah, you create a union. Sure, right, okay. So you just create the union there, right? So let's let S be the union, right, of these two sets, right? Okay. So I think so far this is correct. This is the S now is the set of all words that either begin with alpha or end with alpha, right? Okay, because those words are going to be in one of these two sets. All right. Now, of course, what we want to do is count S, right? So we've actually formed this set of words, right? But we still don't know anything about the cardinality. Okay. So so I think now we can. Yeah, Eduardo. Oh, just to distinguish it from the set in part A? Oh, sure, that's fine. Okay, so we can do that.
Unless maybe there's a chance they could be the union.
No, I don't think there's a chance they're equal, right? Okay, because there are words in S that do not begin or end with alpha, like all betas, correct? Okay, so all betas is a word in S, but it's not in the union of these two sets, correct? Right. So there, it's not S and S prime are not the same. All right. So that's for sure. All right. Now, however, now we have to count S prime, right? Okay. So so now we have to deal with models. Okay. So now you can help me again here, right? Okay. So because I think you were thinking of M prime as actually our model for M prime, right? All right. So what can we use as a model for M prime? And let's go back to thinking about integer segments and so forth, right? Okay. So so what do we know about these words M prime, right? They all begin with alpha, correct? So alpha is fixed, right? Okay. So all you're really worried about there is what? That's right, the four other elements, correct? Right, okay. So you're really only interested in the four other letters, right? Okay, that form the rest of the, four other letters that form the rest of the 6 letters in the word, right? Okay, because there are 6 letters in the word, right?
Just the last letter.
So what is a set there that is a model for M prime? How many letters can you use to form the rest of the word? Alpha's already been fixed, right? Because these words begin with alpha. So how many letters do you have left to choose from there? 4, right? Okay. But how many letters are you going to pick there?
I don't think that's right. You can still have alpha in the middle.
Yeah, you can have alpha in the middle somewhere.
Oh, I see. Right. Okay.
Yeah, in between is what I mean.
No, I see. All right.
So you have to also count alpha.
Oh, yeah, you're right. So I do have to count alpha. Oh, well, that makes it easier, right? So this is actually going to be what? 5, right? Okay. Because I can still use alpha again, right? But raised to what power here? 6th, right? Okay. Just raised to the 6th power. Now, why is that? So think of what an element of this set looks like, right? Okay. What does an element of that set look like? No, just this set. Yeah, so just make up something for me there in that set.
1, 2, 3, 4, 5, 4, 5.
All right, so 1, 2, 3, 4. How about all 4s at the end there? Will that do it? Okay. All right. So what word in this set does that tuple match? See, this is a correspondence, right? So if I give you a tuple out of this set, you have to tell me the element that matches, correct? So what word in this set does that tuple correspond to? It's got to start with what? Alpha, because all these start with alpha, right? And then, what is this telling you? Which letters to use after what? After the first alpha, right? So this word would be what? We'd start with alpha, and then what would come next? Alpha, beta, gamma, delta, delta, right? Okay, there you go, right? The what now? We'll get there, right? Okay, but we haven't got there yet. Okay, so because I'm just trying to count this set, right? I'm just trying to build up this set. What about m double prime then? So what's a model for that one?
That's still going to be
Same one, right? Okay, that's exactly the same model, right? Except, what word does, see, that's still in that set. Now, in this case, right, when you're using this as a model for m double prime, what word does that correspond to? Right, okay. You're assuming alpha's in the last position, correct? So you only have to worry about naming the letters in the first 6 positions. So this would be alpha, what is it, beta, gamma, delta, 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 and then the alpha gets, at the end, gets attached automatically, correct, right? Okay. All right, so we have a model for this set, right? We have a model for this one, and now we know the union of these two is this. Now, what I would like to say is what? Then the cardinality of S prime is how much here? That's what I'm hoping, right? Right, okay. That's what I'm hoping for, correct? Okay. M double prime, right? Okay. But unfortunately, that's too big, right? Okay. So what has gone wrong here? So if this were correct, then I'd be home free, right? We would just take twice the size of these set. This is 5 to the 6th power, 5 to the 6th power, right? Double 5 to the 6th power, and then you're done, right? Okay. But Eduardo, what went wrong? What went wrong?
Double counting.
Yeah, what did I double count? So, unfortunately, what has been double counted here? Yeah, the intersection, which in words is what? That's right, words that begin and end with alpha, right? Okay, so I have to account for words that begin and end with alpha, because those words are in this set, right? But they're also included in this set. So if I just add the cardinality of these two sets together, unfortunately, those words have been double counted, right? Okay. So, but that's all right. I can fix my, I can fix this as well, right? Okay. And but I can definitely fix this equation, right? Okay. Easily by doing what? So what do I want to subtract off here? Right, yeah, so y'all are anticipating the new version of the inclusion-exclusion theorem, but I just want to say this in more primitive terms. What set here have I double counted? Right, so in words, that's what?
The words begin and end.
Yeah, words that begin and end, right, with alpha. Right? Because they got counted in this set and also got counted in this set. Well, all I have to do is subtract that off, right? Okay? Because those words were double counted, but I've got to figure out what's the size of this set. What's my model for this set then? Ah, there you go, right. Okay. It would be this cross product, right? So if you pick a 5 tuple here, correct? If If you pick a 5 tuple out of this set, it's easy to see what word that corresponds to, right? Okay. It would be alpha, and then, right, the letters that match the numbers in your 5 tuple, right, and then end with what? Alpha, sure, okay. So we know how big this set is. We know we double counted that when we added these two cardinalities together, so I just have to fix this by subtracting that out, right? So I have to add one little extra part in here, and that's subtract off m triple prime. Well, what does that turn out to be then? So it's twice what? 5 to the 6th power, right? Minus 5 to the 5th power? So that's a long way from, I think that's a long way from 5 to the 7th power. Okay, so, because this number is already a lot smaller than 5 to the 7th power, right? Which was the original size of s, and you're even subtracting off a little bit more. Okay, so there it is. I have no idea what that number is, all right, but there it is in exact form. What now? 28,125. Oh, perfect. Okay, so 28,125. All right. Okay. Not that many. Well, okay, I guess that makes sense. All right. Well, in this example, that's not quite completely satisfying because the sets were so closely matched with, the model sets were so closely matched with the words themselves. It feels like we were doing kind of busy work, right, to create these set models. But now here's a case where here's a case now where the model and the thing itself, the set itself, the items in the set itself are not going to look the same, okay? What now? Oh, yeah, let's skip C. All right. That's a good problem for you to think about. It's pretty easy, I think. So alpha, beta, gamma, 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 gamma. So that's is that 7? Yeah. All right, so that's a word in our set. And our set has a lexicographical order, a dictionary order, because the letters have a dictionary order, right? Okay, alpha, beta, gamma, delta, epsilon, in that order. So we want to know if you arranged all of those 7-letter words into a dictionary, how many would come how many would come after alpha, beta, and then 5 gammas, all right, in that dictionary. So you can think of this, there's a couple of ways actually to go about this one. But I want to get to this next example, so before we run out of time. These two examples are, again, examples where the model and the set don't so closely correspond. All right, so how many teams of any size, and we can start including 0, by the way, if we want to. So how many teams of any size, and then we can just take off the 0, can be chosen from the class. So we have 20 people in the class, right? Okay. So we want to pick a team out of the class, but we're not limiting the size of the team. So it could be a team of just one person, or it could be all 20. All right. It could be the team. All right. And just to we can always subtract off that teams of size 0, of which there's only 1. We can worry about that later. So don't have to make that, initially don't have to include that restriction that team has to be non-empty. Of course, kind of stupid to have an empty team, but we don't have to worry about that restriction immediately. So how many teams can be chosen from the class? Ooh, all right. So how do we do that? Okay. How are we going to think about that? And then we can think about, suppose we want the team to have size 5. Okay. So how would that be? Different? All right. Here's my suggestion. Okay. We'll start with a really simple set. Okay. So do we? So this can be. This is the set of teams. Let me go ahead and give that a name. Right. So I'm going to begin with this set. That's a pretty easy set. Obviously now, this is not a model for this, right? This set has how many elements in it? Okay, yeah. I got too small there. Let me try this. Okay. All right, so that has how many elements in it? Yeah, well, yeah, one's a little bit too small. All right, so that has just two. Clearly, your set of teams has a lot more teams in it, right? Because you could have the team of everybody. That's already one team. Or you could have the teams with one individual on them. That would already be how many teams? Yeah, that's 20 teams with one individual plus the team of the whole class. That's already one team itself. So that's already 21 teams, right? So this set and this set obviously are not models for each other, right? Okay, but I'm going to build my model for T from this set, all right? And here's what I claim it is. So for the model set, let's call that T prime. So there's what T prime is going to be. Huge, right? Okay. What's the cardinality of T prime? Yeah, what's 2 to the 20th power? We all know what 2 to the 10th power is, right? Okay. 1,048,576. All right, so that's what I claim is the number of teams, including the empty team that we can create from the class. A team of any size, including the empty team. So 1 million possible teams. Wow, that's a lot, okay? Because we only were thinking initially there of 21 possibilities, right? Okay, but there's actually a huge number of possibilities. Now, what does T prime really look like, right? Okay, so what does an element of T prime consist of? So again, I'm claiming that's a model for T, right? Okay, but what do the things in T prime look like? Yeah, they're 20 tuples, right? Okay, so our favorite sort of thing here, tuples, right? Okay, so they're going to be 20 tuples, and how are you going to fill in the coordinates there? Yeah, 1 or 2, right? Okay, so you might have 1 and 1 and 2 and 1 and 1 and 2, right? Down to this 20th coordinate might be 2, okay? Now, right, so of course we're trying to convince ourselves that there's this one-to-one correspondence, right, between the set of teams and this model that I've created, which are these tuples, correct? Okay, so that's where the key point is. How is it that a tuple can correspond to a team? So if I give you a tuple, if I present one of these tuples to you, could be all ones, could be all twos, or could be some mixture like this one, right? Okay, how do you take that and create a team from that? From the class. So what information could that tuple be giving you about the team?
How many people are in the team? Yeah.
Exactly right. Okay. So you said what? 1. Yeah, 1 if that person is in it, and 2 if that person is not, right? So you do have to assume that I didn't make it explicit here, right? But you also have to assume that you have a correspondence between what? The people in the class and the position, which is called in a tuple what? The coordinate, right, okay? So, yeah, I didn't make this clear, right? But every person has to match a coordinate, okay? Well, how many coordinates do we have? 20, right, okay? So essentially we have to assign everybody in the class what? A number, right, okay? That's right, so I've turned it into numbers here in kind of doubly, right? Yes, so we assign each person a unique number from 1 to 20. That's obviously easy to do, right? Okay, because why? What's the cardinality of the class? 20, right? Okay, so we know there's a one-to-one correspondence, right, between the 20 people in the class and an integer segment 20, correct? Right, okay, integer segment with 20 elements in it. Once you've done that, then the meaning of the tuple, right, becomes clear, right? So let's go back and say that to me again. This means what in your reasoning? This means what? So yeah, but who is he? Person 1, right, okay, could be a she, by the way. So person 1 is on the team, right, okay, and this means is on the team, right, okay. What about here, though? Not on the team, right? Person 4 is on the team. Person 5 is on the team. Yeah, that's right. Person 6 is not on the team, all the way down to person 20, right, okay. Not on the team, right? Okay. So you see how that correspondence works, right? Okay. So for every tuple, right, you can build a team from that. That gives you a recipe, right, for creating a team. How do you not get the same team twice, though? Yeah, Kaylee. But what was your question?
So because of the way we've done it, there can be teams of any size between, well, I guess since we haven't counted it out yet, 0 and 1.
Yeah, we could get 0, right, if we were unlucky enough and all of these coordinates were what? 2s, right, okay. That is a tuple in the set. That means no one's on the team. Or we could get everyone on the team by hitting the tuple where all of these are what? 1, right, okay, yeah. But you cannot have, right, different teams. You cannot have different teams corresponding to the same tuple. You cannot have different teams corresponding to the same tuple. Because if teams are different, how must they be different?
Every coordinate is...
No, if I just pointed out 2 teams and said, are these the same 2 teams or not, how would you check that? Yeah, you would go person by person, right, and see if that person is on the team or not. And if they're not the same team, what must happen eventually if you're making that person by person check? Yeah, that's right. Eventually, right, if you're checking person by person to see if that person is on both teams, correct, right, to see if the teams are the same. Eventually, if they're not the same team, you'll hit a person, what, who's on one but not the other, correct, right? That's got to be the case, right? You'll hit a person who's on one team but not the other. But then what's going to happen in that tuple that matches those 2 teams? The number will change, that's right. So you will not have the same tuple, right? Do you see that, right? So I cannot have different teams matched with the same tuple. That's important, right? Okay, I've got to have a one-to-one correspondence between the tuples and the teams. I can't have 2 teams with the same tuple or 2 tuples that give me the same team, right? But I think that's true. So indeed, right, these 2 sets correspond to each other, right? So they have the same cardinality. But someone just told me, right, it's 1,000,000 and something, right? Okay, so we know what the cardinality of T is, right? Oh, yes, right. I must take out 1, correct? Okay. So T there is 2 to the, what is it, 20th power, right? And then subtract what? 1, right. Okay. For the empty team, which we wanted to exclude. So that's what I was trying to point out to you guys earlier. Sometimes you have to monkey a little bit with your set models, right? Okay. If they're off by a little bit, basically the correct model, but off by a little bit, you may have to subtract a couple of elements, or sometimes you may have to add in 1 or 2 elements that you did not, you missed counting. Okay, that's fine. All right. All right. Woo! Quickly, how many factors of 1800 are there? So actually, how many divisors, I should say, of 1800? Positive divisors of 1800 are there? All right. So how many numbers divide evenly into 1800? I can think of 2 of them immediately, or 3 pretty quickly, right? Let's call this D. So divisors, only positive divisors of 1800. So you know this includes what? 1, 1800, right? 18,000. I wonder if I really wanted 18,000. 1 in 18,000. And what else there? 2. Right, okay. Yeah, 5. 100 will go in there, correct? Okay, 1,000 will go in there. 18. All right, so we have a bunch of them. There's a bunch, right? Okay, but clearly there's a lot, right, of divisors of 18,000. Okay, so how can we count all of those, right? So what sort of model are we going to build? First thing you better do here is use the fundamental theorem of arithmetic. You know what the fundamental theorem of arithmetic says?
It's been a while.
Not sum of primes. Product of primes, right? Yeah, that's right. So, yeah, every number is the product of primes, okay? That's the fundamental theorem of arithmetic. Incredibly useful in arithmetic, sure, right, okay? So, let's write down the prime factorization of 18,000. That's the place to start, okay? So, writing down the prime factorization of 18,000. Oh, y'all are going to, that's right, so y'all are going to have to figure this out for me. What is the prime factorization of 18,000? It can't be that hard because... Let's see, this is 18 times 1,000, right? But 1,000 is, that's a power of 10, right? Isn't that 10 cubed? And 18 is, that's pretty easy to write down the factors of 18 because that's 2 times 3 squared, right? 2 times 9? So you've got it to this, but 10 is not a prime number, so you can break this down more. Of course, what's 10? 2 times 5. So it looks like you will have 3 factors of 2 here, right? And 3 factors of 5. So altogether, we have, what, 4 factors of 2, right? These 3 plus this one. And then 2 factors of 3, and then 3 factors of 5. That's it. So there's the prime factorization. That's pretty easy to write down, right? So it's 2 times 3 squared times 5 cubed. Okay. All right, so... Well, guess what? If you're going to have a divisor of 18,000, it's going to have to involve a power of 2, or a power of 3, or a power of 5, right? Okay, not or, it can be and as well, right? Okay, but so if you have a divisor, you know, what's the biggest power of 5 that can divide into it? Yeah, if you have a number in this list, what's the biggest power of 5 that can divide into that? 5 cubed, right? Okay. Yeah, it can't be any more than 5 cubed. What's the biggest power of 3 that can divide into that? 9. And what's the biggest power of 4 that can divide into that? Now, what's 2 to the 4th power? 16, right? Okay. Yeah, 16, right. Okay. And so the biggest power of 2 that can divide into any one of your divisors is 16. All right. But of course, it could be as low as 1, 1, right? 1, 1, 1. That is a power, 1 is a power of 2. It's 2 to what power? And 1 is a power of 3 and also a power of 5, right? 3 to the 0th power. Okay? Does that give you all enough clues there to figure that out? So you've got, if you're going to have a divisor of 18,000, you've got to build it from these factors. Right? Okay. 4 possible factors of 2, but maybe none. 2 possible factors of 3, but maybe 0. And 3 possible factors of 5, but maybe 0. But you can't go over 3 factors of 5, or 2 factors of 3, or 4 factors of 2. Does that give you a clue then of how to build the divisors? Okay, well, we're out of time, all right, so we'll have to bring that up next time, okay? All right, so this is going to be, so here our set model again is going to look a little bit different from our set, but there'll be a recipe for taking an element in the set model and building an item in the set. That's the key here. All right, now, this is kind of the set theoretic model of counting, but we want to talk about the algorithmic model of counting, all right? Algorithmic model of counting means I have some method, step-by-step method, an algorithm that I can use to build an element of the set, right? So I know a scheme for building an element of the set. Can I figure out how many ways I can execute that scheme? If that's true, then I'll know how many elements are in the set, right? That's the second way of counting, okay? All right, that's the one that you're going to be more familiar with. Okay, well, we'll continue that on Wednesday.